Today in Finite State Morphology, we will continue our examination of two-level morphology by showing how finite state transducers defined in twolc can be exported into XFST and then re-exported in a format that can be imported into FOMA. In the preceding lectures, we showed how to define a small toy grammar in the two-level formalism and then export that in a binary format that can be read in by XFST. As a refresher, here is the grammar. We've defined an alphabet that allows A to go to A, allows A to go to B, allows B to go only to itself, allows C to go to A, and allows C to go to C. We then wrote a rule that restricts some of those rewrites. Specifically, this rule states that in the context where the preceding upper-lower pair has B on the lower side, regardless of what the upper side was, then A may only be rewritten as B. Similarly, we wrote a second rule that restricts the context for C. Specifically, we said that in the context where the immediately preceding pair of symbols has A on the upper side, regardless of what was on the lower side, then C may only be rewritten as A. This restricts this from happening. We then used the twolc program to export this machine into a binary format by reading the grammar, compiling the grammar, and saving the binary. We can use the load defined command in XFST to load these two machines. The machines have spaces in their names, so if we want to work with these machines, we will have to escape the spaces using %sign as the escape symbol. We can use the write dot command to see a visualization of the machine. And a visualization of the other machine. What, though, if we want to work with one or both of these machines in FOMA? Well, XFST allows us to use the AT&T finite state machine file format. So the machine that is on the stack can be written using the write AT&T command. If we have a transducer, which we do, we will need to use this notation, where we provide a target file name and then two other files that are required, but we won't be using them. One for the input symbols and one for the output symbols. Here we see the machine. Other is being used for out-of-vocabulary symbols. However, FOMA uses a different notation for the out-of-vocabulary identity symbol. And so before we import this into FOMA, we're going to replace other with the equivalent symbol used by FOMA. We can then load FOMA. And we can see that we have successfully imported the machine. Let's go back to XFST and export each of the machines. After doing that, we will import them each using the command that we just used, read AT&T, into FOMA. We will look and see what each of these machines do individually, and then we will intersect them to show what twolc is doing behind the scenes. Back in XFST, we're loading the defined binary file. Remember, the binary file was created by twolc. In this file, there are two machines, the A to B machine and the C to A machine. We're going to push the A to B machine, remembering to escape the spaces. And then we're going to write it to AT&T file. Call it A to B .AT&T, and we are required to specify the input symbols file and the output symbols file, even though we will not be making use of them. Now let's do the same thing for the other machine. Push C to A, remembering to escape the spaces, then write to the AT&T file format, C to A, we're now going to edit these files. Replacing other with identity symbol, saving the file. And then doing the same thing in the other file. Having made that minor change, we can now load up FOMA. And use the read AT&T command to read the A to B machine. We'll then define it to give it a name. Next, we'll read the next file. Notice that it's automatically pushed onto the stack but not given a name, so we will use define to give it a name and pop it off the stack. Now let's look at these individually. Notice that when we apply down on this first machine, the value C, we get both C and A as valid options, because this machine does not restrict what can come at the beginning for C. However, it does correctly change any A to B if the preceding symbol on the lower side was B. If we push C to A and try apply down, we will observe that applying down on C restricts us to C. But the symbol A is allowed to be A or B. And if C comes in the appropriate context with a preceding upper A, then it is rewritten as A. If we intersect these two machines, and we apply down, then we get the desired behavior, which is what 2L does for us. We see now that the restrictions of both machines are being applied, and we get the result here.